Okay, now that we have defined velocity, let's relate the following. Okay, so you saw that derivative of the position is velocity. Derivative of the position is velocity. Now we'll see what the integral represents. So we had defined displacement. Now the time derivative of the position is given by the velocity. And now if you integrate both sides of the equation, so if you plotted velocity as a function of time, so if you take the integral of that, so here's this equation, dx by dt is vx, you integrate both sides of the equation, this would be the area under that curve. We saw that in our calculus primer. And by the fundamental theorem of calculus, when you integrate a, a full derivative, what you get is the function evaluated at the endpoints. Okay, so what we're saying is this area under the curve is this displacement. So if you take velocity as a function of time and take the integral of that, which will give you the area, that's equal to the displacement. Now let's define acceleration. You are accelerating when your velocity changes. So change in velocity divided by the time over which this change happens is the average acceleration. Okay. If there is no change in velocity, acceleration would be zero. If this was zero, that would be zero. Now you can go to this link and look at objects that accelerate. Okay. So for instance, here's the position as a function of time. For this motion, the velocity is constant and zero for the first second, and then it's increasing. So the velocity is increasing, and so the object is accelerating. The velocity is constant here, and it's not accelerating. The velocity is changing here, and it's decelerating. And that's what this graph shows. In this portion, the velocity is not changing, the acceleration is zero. Here, the velocity is changing and the acceleration, and it turns out that the acceleration, the slope of this line is constant, so the acceleration is constant. No acceleration here, acceleration is zero, and the acceleration is negative here. So what we're interested in is instantaneous acceleration. Instantaneous acceleration is the average acceleration in the limit delta t going to zero. And that's equal to the time derivative of the velocity, which is the second derivative of the position as a function of time. So here's a quadratic function of time. The position is a quadratic function of time, and this is a parabola. For such cases, as you saw, so for quadratic functions of time, the velocity is a linear function of time, and acceleration would be dv by dt would be constant. So the acceleration is, if the position is a polynomial, the acceleration is a polynomial of degree 2 less. So for a quadratic, acceleration would be constant. So for this motion, acceleration is constant, and velocity is a linear function of time. Alright, so you saw that if you plot acceleration as a function of time, the area under that curve gives you the change in velocity, gives you the velocity at the end point minus the velocity at the initial point. So this area, which is equal to this integral, is the change in velocity. So what we are showing here is how to obtain velocity from given the acceleration as a function of time. What this graph shows you is the following. So purple vectors represent acceleration and red vectors represent velocity. So if the acceleration vector and the velocity vector are pointing in the same direction, the magnitude of the velocity increases. That means your car is speeding up. In this diagram, the acceleration is zero, and so the velocity remains constant. In this setup, the acceleration is pointing in the opposite direction of the velocity, and so you can see the magnitude of velocity is decreasing, and of course this means you're braking, so you're stopping, coming to a stop. All right, these set of graphs, so you are to match these graphs, so velocity versus time. Remember, acceleration is dv by dt, meaning the slope of this line, and the slope of this line is constant, so this acceleration goes with that. For this graph, this dv by dt, the slope is increasing, and here's an increasing acceleration, so that graph goes with that. For this graph, acceleration, again, slope is constant and non-zero, and then it's zero here. So this graph goes with that. So in a 1D motion, when the acceleration is constant, and this is the case we'll mostly deal with. So let's go back to the example. So when acceleration is constant, that means the position is a quadratic function of time, and velocity is a linear function of time. This is just a made-up example, but that's generally, that's always true. So we'll mostly be studying motion with constant acceleration. Acceleration is constant, velocity is a linear function of time, and position is a quadratic function of time. So here are the four kinematic formulas we'll use. Uh, these four formulae are valid when acceleration is constant. So this is the final velocity is equal to initial velocity plus acceleration times time. So this is velocity as a function of time. This is displacement, final position minus initial position, is equal to average velocity times time, and average velocity is final velocity plus initial velocity divided by 2. The more useful formula is the displacement is initial velocity times time plus 1/2 times acceleration times time squared. And this gives you the final velocity as a function of displacement. Okay, so these are the kinematic equations that we will use to solve problems. Of course, this slide derives these four kinematic formulas. Okay, so you can go through this derivation. Now, one of the few motions that you encounter with constant acceleration is object traveling under the influence of gravity. So if you toss a ball, the acceleration, only the neglecting air resistance, the only force acting on this ball as it's falling is acceleration due to gravity. And the acceleration due to gravity always points downward, and we denote it by g, and the magnitude of the acceleration is 9.8 meters per second squared here on Earth. If you find yourself on another planet, of course the acceleration due to gravity would be different. Okay, so the magnitude of this constant acceleration is 9.8 meters per second squared. All right.